All right, hi everyone. Sorry for the quick delay. We still had some organizational stuff to do, but now we're finally ready to start. So thanks for the two amazing speakers that are here as well. And before we actually jump into the talks of the speakers, I would like to introduce myself, Hasty, the company that's organizing this event, and also talk a few words about why we actually do this event. And I'm Tobias. I'm going to be the host for today. And what I do here at Hasty is that I help our clients to succeed with their Vision AI projects. And I really work a lot on the strategic aspects of machine learning in production. And we started the series of events because what we realized is that everyone is talking about, hey, machine learning in real life. Machine learning in real life is so different than from research. And you know, there are all the MLOps challenge, data-centric challenges, and so on and so forth. But there's actually very little exchange about actual projects that make it to production. And what does it actually mean to be data-centric? What does it mean to have an MLOps pipeline and all of those things? And yeah, this is why we started the series of events. And yeah, we started it originally in Germany with great success. And so now we're starting this as well more regularly in the US. And yes, what do we do at Hasty? So what do we actually do at our company that brings us to the position to organize those events, to talk to people about how they do machine learning? And this is what I'm going to talk to you in a few slides, but really more on a high level. And then I'm going to hand over to the speakers, as the event shouldn't be about Hasty too much in detail, but about the speakers and what they do. So what we do at Hasty is what I already teased, is that we help teams to build Vision AI applications and to get to production reliably, time efficient, and we do that by enabling an agile data-centric workflow. Just some high-level facts about us. We are a startup from Berlin, Germany, and we come from German manufacturing. So 5 years ago, we started to work on all kinds of QA problems, automatic assembly problems, and we were applying research to reality. But what we realized is it's much, much harder than we thought, and we ran into a lot of problems. So we started building our own tooling, and this tooling turned into what's Hasty today. And we got funded in 2020 from Shasta Ventures mainly, the investor from San Francisco. And yes, by today we are 30 people, or 34, I believe, actually. We have over 12,000 users around the globe, and we really work together with a broad range of organizations, from small startups, research institutions like Stanford, Harvard, and the biggest corporates of the world. And yes, and so far we've been mainly operating in Europe, but now with COVID opening up again, we're able to travel, we're coming to the US regularly and actually getting more and more clients here as well, and are expanding over here as well. So what do we do when we say Vision AI, and what do we mean by that? So Vision AI is essentially technology, right, that teaches your computer, your machine, to see the world. I think everyone here will know that. So I don't need to go into all of the applications you can do with Vision AI and all of the use cases you unlock with Vision AI. But if you look at the adoption curve of it, what you will see is that the hype around 5 years ago, when research said, hey, we figured out object detection, we figured out instance segmentation, we figured out all of those traditional computer vision problems, the hype in the business world was huge. You know, like this one quote from McKinsey, 20% of all activities are now automatable. There is so much trillion market cap, and now the world will be perfect. But what actually happened is that when teams tried to apply the technology to real-world problems, most teams failed, including ourselves. And this is a very normal movement because, you know, when you take research, apply it to practice, things don't work the same. So you need to figure out how things work differently and how you need to figure out processes and approaches to make it work in production, to real life as well. And what's changing now is that a small group of teams actually emerges that is getting this right. And this is by following a data-centric approach. So what we mean with data-centric, and the question is like, what changed? You know, like, why are teams now succeeding? Is that in traditional computer science, you would view algorithm and data as two separate things. So, right, so you would say, no matter if I post a picture of an image or dog, it should be displayed the same way in my application. And this is also how machine learning research is done. You take a fixed data set, COCO, ImageNet, Pascal VC, one of the big research data sets, and then you try to beat the algorithm of the other guy and be 0.5% better. Whereas if you now go to real world and you go to practice, what you would want to do is you would want to work on your algorithm and data in tandem, because like the data actually influences your algorithm. It's not only about, do I have the right model, but it's also, is my data clean? Is my data representing the real world? Is it like the right data for my use case? And this sounds trivial when you say it like this, right? Like when you put this on the slide, everyone is saying, yeah, of course, that's machine learning. But really embracing the consequences of that and understanding what this means for teams that go to production, the consequences are huge. So teams that follow the old way of thinking, this model-centric way of thinking, what they would do is they would start, first with all of the data tasks. So that's like the bright blue things over here. And they would collect 10,000 images. And then they would say, okay, now we labeled, like we have 10,000 images. We labeled the images. Now let's train a model. And like this process, when you want to label 10,000 images, that takes you 100K or 200K, 300K, depending on complexity, and several months. And then they train the first model just to realize, oh, we have a mistake in our data strategy. We misrepresented a certain class. We should have used a different annotation strategy, so instance annotation, so object detection. We should have tried a completely different approach of training models, et cetera, et cetera. But then, like they already spent so much money and so much time that they need to kill the project because they don't get investment anymore or buy-in from the management. And this is exactly what explains this 87% failure rate, and it all comes from this very simple way of seeing machine learning where you say, no, model and data are two separate things. But in the ideal state, and this is now leading us to what we do at Hasty, you would work in a way where instead of getting this feedback 3 months in the project, you get feedback in the first day. And then you keep working and you actually say, okay, this is actually really working out. So let's go down that route and let's actually invest by having this feedback, taking these ideas from agile software development. And what you would do is like the ideal process would say, okay, you have 10 images, you train your first model. It's gonna be bad. Like don't get me wrong that I say 10 images, you have a good model. But then you retrain again after 100 images and you see the data, you see the difference. And you see, it's understanding things. And then you do the same thing after 150, after 200, 250 images. And you constantly get this feedback and you say, okay, actually, it's really working out. It's getting better. It's getting smarter. So let's go down this route. Or if you say it's just getting worse all the time. So something's wrong with our data. Or something's wrong with our data strategy. Why is that? And then you find the edge cases. You can actually readjust and reframe. And the key drivers that we see at Hasty, that we saw like in the hundreds of projects we were working on, to have such a workflow is A, that you have a seamless pipeline between the tasks. So instead of labeling, and then you need to wait weeks days to write like a data loader, to write the data integrations. You should like be able to switch between data and model tasks with a few clicks. Same goes for automation, right? Like the more you can automate in each single task, the faster you can iterate, the faster you can run through the loop. And then last but not least, the key point is that we see is that you have this early deployment, what I just mentioned, right? Like really take a model that's raw, that's early in the process, test it, and don't train for days and have 10,000 of images, and then you go to production and try it out. And this is like the last slide I'm going to show, and also the last thing I'm going to talk about. But this is essentially what we are building at Hasty. So this workflow we just described, we enable this workflow out of the box. And you don't need to build your own labeling pipeline, training pipeline, monitoring pipeline, but you get all of that in one tool. And we do this by automating the labeling in a way where you get feedback on your labeling strategy after image 10. That's when it starts. We have smart data cleaning features because garbage in, garbage out. You will never have a good model on bad data. And you're surprised how bad data is. Like even in the big research data sets, we did a small experiment with Pascal VOC, and we found, like, we just spent 1 week of cleaning data with this feature. And I think this 1 week, we fixed 6,000 annotations. And by that, we could improve the model performance by 13%, right? So this data topic is huge. And then last but not least, you can train your custom models. But this is what I'm going to leave it with. So again, like, this shouldn't be about Hasty. I just wanted to give a short introduction of what we do at Hasty, and how we get actually to this position, that we meet people like Ryan, like Nico, who will speak in a second. But instead of me just talking more about how awesome Hasty is, I actually want to really give the stage to you guys and to talk about, not talk about those concepts I explained on this abstract level, right? Like, you get this everywhere. But actually, what does it mean if you work on practical projects? How do you apply this to real-world applications? And the first speaker will actually be Ryan today. I will skip a very long introduction, but just as a quick introduction, Ryan is part-time researcher at NASA JPL. The other part of his time, he's working on his own startup. Both are very, very fascinating projects, very cool projects. But today he's going to be here as the role of NASA. And what he's going to share with us are essentially how NASA is using computer vision on Mars, and then what he learned from that. With that.
Thank you so much, Tobias. I'm very excited to be here. Thank you all for coming here. First, I want to thank, the Hasty AI for hosting this event, and the ML IRL, I believe. And so today I want to talk about, the first part of the talk is going to be about some of the work that I've been doing recently at NASA JPL, and it's related to the Mars Rover, and the second part is going to be related to the Opal AI. February 18, 2021 was a special day for me. In fact, we observed that the Mars Rover, the Perseverance, successfully landed on Mars, and we were really happy about this situation. However, it was also such a dilemma, because we were able to see the rover outside our office in 3D. We were able to interact with it, and we could have seen it whenever we wanted. However, things changed after that day, because the data that we were getting was 2D, and it was like suddenly our 3D world converted to the 2D, and that was a shift, right? So when such a thing happened, so here is the rover that you can see, a selfie that the Perseverance took with the Ingenuity, the rover. And this rover that you see is the size of a SUV. If you don't have, you probably cannot capture the size of it in 2D images, but it's mass, it's huge. And now we need to interpret the scene from 2D images. So I wanted to see how we can build a technology that we can have a view like this, but in 3D. There are lots of applications associated with this technology, like 3D scene reconstruction. And what we have and what we see at NASA, there are lots of technologies that we can leverage. One is, for the navigation tool, and in the navigation tool, as you see in this video that it should play, but it's okay, I can continue the presentation. But what it is here that you can see is the rover, so one of the rovers got stuck in a sand dune, and that was because there were some problems with, what we observed was a sand, covered some holes. And the navigation team that were in charge of navigating the rover and make sure that it's safe, they were unable to identify that there is a sand in that area and navigate it safely. So one of the rover got stuck, and that was like a big deal. Or the other thing that I personally work on these days is Curiosity rover, and we see the wheel is damaged significantly, and unfortunately, it went to this like a safe mode, and that's why maybe I'm here. So I got free time, and then I was able to come and travel here to Boston. But these are the navigation tools that we also use a JPL, so it's semi-autonomous. So we also have this autonomous navigation tools that it can reconstruct the scene around the rover, and also the analysts and the people can visualize, the obstacles around the object. So the other application, which is very important for us, and especially for scientists at NASA, is how we can maximize the science extraction. So the main goal at NASA is to benefit and help, at least for the technologists, that I am one of them, to help the scientists. And in this situation, we want to maximize the science work that we can get. And one solution for it is using different technologies. So we have emerging technologies such as the AR and VR, which they can use. But one obstacle and bottleneck that exists is the fact that we are limited in terms of how much data we can transfer back to the Earth. And so that's why compressing the data in 3D and maybe visualizing it for the scientists could be really helpful. And whenever they wanted to see something very exciting in higher resolution, they can query those data sets and get it back, because it's time consuming. Even with the speed of light, it takes 15 minutes to get the data back. And then there are some bandwidth issues that we have, which is related to the systems that we have. So the solution we provided to address these two problems, especially for NASA, was using NERF technology, which is a very recent and new work in deep learning community that stands for Neural Radiance Fields for View Synthesis. This work came out like in 2020. The first paper came out in 2020, and it had a really interesting idea. So it combined two concepts. The first concept was the overfitting concept, in which your neural network wants to overfit to the data set that it has. So it's, the first paper was called like implicit neural representation, and in such situation, you don't need a huge data set. You just need one data set, and that's your training data, and you try to overfit it to do it. So the first application associated with that was for image compression. And in 2020, that like the NERF paper combined this with ray tracing, which uses a similar concept, but it tries to overfit to a single instance, and it does it by estimating the color and the color in each scene and the value of the volume, and it tries to fit, in fact, a continuous function that is represented in 5D, which is the X, Y, Z, and the 2D viewing direction that we have. And the output is going to be the color and as well as the volume density. So that was one of my favorite works that I have seen, recently in the deep learning literature. And we wanted to give it a try. So in the next slide, you should be able to see a video. However, you cannot see it, and due to the yes, if that's yeah, I can quickly do that. Sorry for any inconveniences. So I can quickly show it to the audiences. So if I plug it in, is it going to be viewed online too, or is it shared to me? Yes. So what we so here is the video. Then should I? Yes. Okay. So what's going to happen, and what we are going to see here is this video that we're going to do view synthesis from the I think it's better not to. Okay. So it is getting shared. Okay, cool. So what we see here is a view synthesis from the model of the Mars Rover on Mars at JPL, which I just grabbed my phone. I took a video, and send it back, process that on the cloud. So you can see a very high resolution, scene from the rover in this video, that the view synthesis video. And of note that it was only RGB values were used, and the whole process took 5 minutes, which such a thing before used to take days to 2 years ago. Right? Not like with the first near field it would take a lot of time, but now all of the training happens in 5 minutes. So one thing that you can see in this second video is, okay, the one side was captured and reconstructed very well, right? The other side is not that well, because when I was rotating around this, there was like an obstacle, and I was not able to get more images on the other side, and I was not able to get some images from the top. So the ray tracing is really important, right? You want to get as many photos as you can from different scenes. And here are the 2D images that we can see from the from our approach, which we call it MRF. And one cool feature that you can see, you look at the trees, right? You hit the glasses. It's very clear, right? You're going to see lots of details in these scenes. And we also compare it to the other state-of-the-art 3D reconstruction methodologies that are out there, like Apple Object Capture, agile, which is the commercially available software, and reality capture. And you can see in each they're doing very great, right? But in agile, we see the glasses are not really reconstructed in a good situation. In the Apple situation, you are not able to extend it to the large scenes. And also in the reality capture, you see the helicopter is not very well reconstructed. Maybe the rover got reconstructed well, but the other scenes are not. And we wanted to, in fact, go one step further. So I had one of my team members in Europe, Lorenzo, and he asked me, can you take a virtual tour? I really want to see how JPL looks like, and how what is the experience. So I took out my cell phone, I took a video, and then we started to process that with our framework. And here is the result that you can see. What I did here, I just walked around, took a video, and then processed that with our algorithms on the cloud. And we are not flying, it's not a drone. So you see some artifacts, and these artifacts are due to the, the ray tracing problem that we talked about it earlier. And just this work, and all of the 3D scene reconstruction took less than 10 minutes. And we don't need more. It's like what we need is the data set itself, right? We're overfitting what we do over time. We're overfitting to the same scene to get details such as the shadows, right? So we want to reconstruct each scene in different camera views. So to me, that looks very interesting, right? And it was one moment that I thought that, okay, the world is changing, and there is a buzzword these days that people talk about digital twin and metaverse, right? And honestly, that's real. What we're going to see that digital twin is going to somehow change how we interact with one another. And as we see the depth sensors are becoming more available, we can see new opportunities. Previously, LiDAR scanner was only limited to certain applications, such as NASA's Mars Rover landing mission. However, with the wide adaptation of the LiDAR sensor and depth sensors, anyone with the latest generation of iPhone Pro or iPad Pro has access to this technology. And this opens up new application and new market segments, which we are very excited to be part of that. One other quick thing that I wanted to mention was, let's think about, elderly people, right? So elderly people can now, with this digital twin concept, can see their sons or grandchildren anywhere and anywhere, anytime, and in different situations. They can travel, to Mars and see each other on Mars. They can do different sort of activity, which is a real revolution. The other thing is digital twin increases the connectivity. One thing that really captured my attention was if people around the world were able to see, what's happening in Ukraine, and they were able to walk around and see what's happening there, it's gonna be life-changing for many of us. Maybe politicians have different, perspective from what happened, what was before and what was after, and they may be able to travel, virtually there and see what's happening. Or many of us, were excited to see what happened in Oscar this year, right? And wanted to see that live and in possibly 3D. And so this is gonna open new market segments and technologies. For me, that technology and application was in real estate, and in fact in prop tech or property technology. And here is the demo of our app. It's called Opal AI Scan to 3D. And what you can do, you can create a digital twin of your environment on the device. You can move around, take a video in the building or in the house, and get the digital twin as you see on the right, like accurate digital twin. Once you have that, you can upload it to the cloud server, and using 3D deep learning technologies and you can and some other AI methodologies that we developed during the past 4 years, you can declutter this environment, find a relationship between the rooms, and deliver an accurate 3D and 2D floor plans to the customers and to the people. So here is the demo of this is the model of our office. Some of our team members are in fact online, and they're working here, and this is my this is how our office looks like, and what you can get in the end is the floor plan, right? The floor plan is going to have lots of applications, such as renovation, such as home improvements, interior designs, and so forth. And this is another 3D floor plan or rendering from one of our other clients that you can see. It's really hard and time consuming to build such a floor plan, like manually. People need to go there, need to go to the job site and take the measurements, each wall manually, and in the end they need to come back and create the floor plan themselves, which with our technology they just need to take a video around the house or around the office and get an accurate 3D model and a CAD model of their spaces. So this is one situation that one of the people that was trying our app, and customers showed what they did compared to the results that we got. For sure, there were some corrections involved, but it shows that there is we could improve and reduce the time and cost of such work significantly by 10x. So in summary, this work, which is based on some of the recent technological advancement, has a couple of features such as accessibility. You just need an iPhone, an iPad Pro to use our app. We're going to provide it in different formats. You can have 3D virtual tour, as well as the outputs that are commonly used by the industry professionals, and also you can get it on the same day rather than waiting a couple of days. The AI technologies that we use have, there are different things that we use. We process the point cloud, the 3D data. We get the RGBD as an input, and we perform, texturing, bringing the color to the 3D model and the 3D mesh. We do semantic segmentation. In fact, we tried many companies and many open source tools to generate a labeling tool for 3D data, and we were not able to successfully adapt or work with anyone. So we decided to build our own. So we developed our own annotation tool, and as well as some other techniques that we use to get the 3D scene reconstruction, floor plan, and the gross living area calculation that can be used by different real estate professionals. And we're gonna have big updates soon, in the next quarter. And you can download our app using this QR code and give it a try, give us the feedback. And we would love to hear what applications can be done with this work. And in the end, I want to remind that for many of us, we had this moment that we leveraged lots of technologies that were used in the space industry, like the Apollo. But now it's a two-way direction. For example, the Mars Rover is running on the Snapdragon, which is a similar chip that is available on your smartphones. And with that, we are able to get, really, we can go one step further and make, it's a two-way direction between, Earth-based applications and space applications, not one way anymore. And I want to thank NSF a lot for their support. So some of these works that you saw was funded by the National Science Foundation, which they help us a lot to create this Opal AI. So they are the main supporter of Opal AI. And also I want to thank all of you for being here, and the Opal AI team and the JPL team. And if you have any questions, please contact me. I would be happy to answer your questions in chat. Thank you so much.
So maybe I actually have one question. First of all, thanks for the talk. I believe, yeah, with the remote people, they don't have questions coming in, but maybe I would just jump in for them. What's interesting for me, or maybe if you could elaborate a bit on, first of all, thanks for the talk. I want to make sure that I don't forget to mention that it's a very interesting way of how you go from research to actually real-world use cases. But one question I would have is, how do you deal with data shift for your segmentation models in terms of saying, right, let's say you trained to model a nice Californian houses, but now you would come to Europe and all appliances look different. This is an extreme example, but maybe a bit more realistic one for you is just you see new appliances, you didn't see before. Because, someone has a special kind of grill or smoker, some special things. What's your approach to deal with that when this happens? And, yeah.
That's an excellent question. And it reminds me what we do in space exploration. So even in space, you have limited examples from Mars or Jupiter or Saturn, and these are new environments, even more extreme than what we have here. For sure, there's some sort of, like a meta learning, we can say. We can leverage the prior experiences that we have on other circumstances and bring it to the new environment. However, one of the topics that we see even in AI is human-centric AI, right? Even for the rover, we don't solely rely on the AI or the computer decisions. There is a human involved, and it's a human AI teaming or human-centric AI. So how we can deal with that problem, we can bring the human or an expert in that area and get feedback from them. And in this situation, we can train the AI to the new environments and adapt to the new environments, and once we are sure that the AI can work in the new environment, then we can put more trust on it and reduce the involvement of the human. But in the beginning, for sure, it's going to be more, and then in the end, it's going to be less. Thank you.
Yeah, makes a lot of sense. We see it differently in a lot of projects we work on as well, where you have exactly this approach. It's not about replacing the human, but it's reducing the work for the human, right? But you still make the decision by human in the end. No. Any questions from the guys here in the room? Otherwise, let's go to the next speaker.
Thank you.
All right, thank you. And then maybe let's just switch that up.
Yes.
Well. So maybe I would start with introduction, and then we will fix the slides afterwards. For the next speaker will be Nicholas Morand, and we met Nicholas Morand while he was doing his graduate degree in data science at Harvard, and he was working together with WildTrack, what he will be talking about in a second, where they try to protect endangered species using Vision AI, and how they do that, I will leave that to Nicholas to explain. But I believe also it's a very, very interesting use case, a very, very fascinating story in terms of how AI can actually be used in real life. And it's a very good sometimes it's hard to explain the benefits, right? And here you see it very well. And at the same time, there are a lot of challenges they have regarding the data, and they are doing some iterations. So we've been working, as I said, together for quite a few months already. So this is, we experienced this process, and I believe it's a very good journey, very interesting journey. So I'm happy to, without further ado, hand over to Nicholas.
Thank you, Thomas. Thank you, Thomas. So my name is Nicholas. I'm actually a machine learning engineer volunteering at WildTrack. And so I'm going to talk about using computer vision to protect the endangered species. So first, about WildTrack, it was founded in 2004 by Sky Abigail and Zoe Jewell. Their main goal is basically to protect endangered species by using a combination of 3 different techniques, which is advanced data analytics, artificial intelligence, and traditional ecological knowledge. This last one is actually related to people, I would say, and skills that they have, and in this case, indigenous trackers. The main objective for WildTrack is actually to develop and apply non-invasive monitoring technique instead of invasive one, and I'll talk about those ones. Also, it's to engage, value, and revive as well the local ecological communities, the ones that have been living with endangered species for many, many years. And finally, the augmented data collection. This is a big thing for us. And through scientific networking, meaning scientists, engineers as well helping us for that, but also just citizen scientists, anybody who is interested to actually help us gather data. Just a few key numbers about WildTrack. We have currently about 40+ projects. This includes multiple species, but also footprint identification, which I'm going to talk about right now, as well as UAV, so any drones, we do also that kind of project as well. In our database, we have about 80+ species that are in our library. 15 of them are using the ML and CV. And we also have 14 using morphometrics, which is the technique that WildTrack has been using in the past with GMT software. And we have about 17 partner universities. We have many corporate sponsors, including Microsoft, Hasty, and so on. And we have about 35+ volunteers, scientists, biologists, conservationists, engineers, and so on. So, about the data that we use, in our case, the data is actually free to find, and if you care to look, it's just on the ground wherever species pass by. And what we do with it is we basically compile a library of all the species, their footprint, with also a ruler. We know the footprint, the species of the footprint, sorry. We sometimes are able to know the sex as well as the individual and which foot it is. This is based also, all those metadata are based on the skills of those trackers who are able to know by their own skills those things. And we were trying basically to reproduce that through computer vision and AI. So the WildTrack has basically been developed a footprint identification technology, FIT. So I want to explain a little bit how it compares to other techniques that are basically invasive. So first, FIT is an ubiquitous data, meaning it's free, it's very easy to access, and anybody can collect them. While other techniques are more trying to locate the species, which is not as easy as it seems. You would think an elephant is easy to find, but they're not big in numbers, and it's a big land, so it's quite difficult, but it's also dangerous. Like at the end of the day, you don't want to try to locate a lion or an elephant and try to face it and get into dangerous situation. So that's one of the big advantages of collecting footprint is we don't have to put ourselves into dangerous situations. But also, like I said, it's cheap because you can just basically take them from the ground with your phone. Large volumes can be taken. If you follow a trail of an animal, you have 4 foot for each animal, and so if you follow a trail, you can have a huge amount of data that you can get. In terms of the other techniques, it's actually quite expensive and invasive. Expensive because you have to have like GPS collars, you also have to have the radio in order with the antenna, you have to have a lot of people, you also impact the animal because you need to sedate them to put the collars, because putting a collar on a cheetah is not going to be that simple. So tagging, collaring, like I said, is invasive, and it's been proven that it's actually negatively impact the physiology and the behavior of the animal. It also impacts their fertility, sometimes their movements, and can also lead to basically death as well, based on studies. The collection on our case is non-invasive. We do not interact with the animal, so that's one of the big advantage. And there is no impact on data quality. Like I said, the tagging coloring impacts their physiology and their behavior, so you're already impacting your data quality right there. In our case, we're not. We're just following the footprint, and the animal is not changing its behavior based on what we're doing. It's based on expert tracking skills, like I mentioned before. So we engage with local communities to help us basically track those footprints. While other techniques rarely do that, so it's actually nice to finally engage and revive those indigenous trackers and their knowledge, since it's a gold mine. They are able to do things that the computer is just starting to be able to do. Like I said, we have different levels on FIT. We are able to do the species, the individual, the sex, the age class, as well as the foot, using CV and morphometrics, while on the other techniques, it's mostly as a species level, and also since it's very expensive and you have only a small subset of data, you're actually not getting the full picture of what's happening. So let's talk about the cool stuff. That's why we're here, and the model flow that we developed. So I actually developed this during my master thesis at Harvard, and with 3 other engineers. And what we did is basically we took an original image, so part of the data collected with the metadata. We detect the footprint by species, and we also detect the scale thanks to the ruler. And the scale, we're getting basically pixel per millimeter, and so we can calculate, thanks to the detection with the bounding box, we can calculate the size of the footprint. All of this are after used for the attribute identification. So we recognize basically which foot, which sex, and which individual it is from. So before being able to get there, we have to label the data, we have to have a real ground truth of data, which is extremely important in our case in order to be as accurate as possible. And labeling a footprint is actually quite complex. It's not that simple. You have basically animals like cheetahs where comparing to the lion that we have here, the cheetahs have their claws showing on the footprint, and it's extremely important for the model. So we wanted to keep a human in the loop approach using experts like trackers, conservationists as well, in order to help us label those data. So that's the bounding boxes in our case. We also used Hasty in our case for faster labeling with the AI-assisted models, as well as quality insurance. We used their AI consensus scoring, which helped us actually find simple human errors like the wrong object class or an extra bounding box or slightly smaller or bigger bounding box, and actually proved quite useful for us. Even using experts, at the end of the day, human error happens, and so that's that kind of technology that actually is very useful for us. So let's talk a little bit about ruler detection and scale estimation. I'm just going to give a very quick overview on that because it's the details would be quite deep, and my colleague who developed that is not here. So let me show you what we actually did. So we take the input image. We detect the ruler. We do a lot of different pre-processing of the image, use the spectral in order to detect the ruler. So you would basically have the capability of detecting both parts of the ruler. And from there, what we do is we actually are, since we know where the ruler is, we can have basically sub-boxes of each part of the ruler and fit a model based on the split of the ticks of the ruler. So what we do is we're able to calculate the number of pixels between each millimeter ticks, and from there we create a full model in order to estimate the scale. Our technique basically is able to have a statistical error of 2%. So quite accurate, and we have a systematic error of about 10%. So what it means for the systematic error is basically mostly due to the way the picture is taken. You might have the ruler in some cases that is slightly bent, so that would affect the estimation because you have one part of the ruler closer to the camera while the other one is away, so the pixel per millimeter is different. So that's that kind of error, but also the way the picture is taken, the way you hold the camera or the phone, depending on the axis, will affect also the estimation. So so for us, it's important that people understand how to properly take that picture in order to avoid those issues and stay at that 98% accuracy, basically. In terms of image augmentation, I just wanted to show you quickly what we do on our side. We use variational autoencoders, but also neural style transfer in order to increase the amount of data that we have. Since we are limited on data, we wanted to make sure we are able to apply this on different ground, I would call, of the footprint. So in this case, we take the input image, we change the style, so in this case would be sand, and we have the augmented image that we can use in our models. So about the object detection model, in our case, that's the species footprint detection. We have 14 object class, so it's the 14 species that we have. I just added one more 2 weeks ago, so we now have 15 actually. On the image classification part of the object detection model, we are able for the label class prediction to get about 99 on train, 98% on test. And as you can see on the confusion matrix, we're able to clearly identify the species and basically even the subspecies. We would have rhino black rhinos and white rhinos. Those two are the same species. So we actually are able to differentiate the subspecies, and we can apply that to more subspecies. Like right now we have the cheetah Southeast African, but we have more cheetahs that we could do, or otters and things like this. The accuracy on the model that we developed, so it includes the classification that I just talked about, but also the localization. We're able to get 95% on train, 80% on test. So one thing to note about this is this actually was developed on Hasty, and what it does not include is the scale. We're hoping to add that in the near future, and we believe the scale would improve, especially for the test set results, would improve the accuracy, as scaling is actually quite important when it comes to footprints. And this leads me to the attribute identification. So in our case, that would be the foot, the sex, and the individual. Just quick show you what I mean is we have on the top part the species detection that is part of the object detection model, and then we have the three attributes, sex, foot, and individual. The sex and foot are the same for any species that we have in our database, and then we have the individual. The individual are actually clustered by species in our case, what approach we used for this, and first about the image count. One thing to note is for our model, we used about 3,900 images, so it's not a lot. We have about 10,000 more that we can add. It just needs to be processed through a specific process for image quality and so on. But basically for the individual, we have about 163 classes for only 1,500 images. So quite limited in data, but we were able to still get results through that. So The two approach we used for this was attribute recognition and image classification. The attribute recognition is basically based on the object detection model, and it's pretty much a multi-label classification type of approach. The main interesting thing here is actually that we have all 14 species in that model. And all 3 attributes. We have one single model to detect all attributes for all the species. So it's quite interesting because we can apply this with less computing power. It's much easier to develop, and it's completely linked on top of the object detection model. It's just one more layer of metadata, basically. The accuracy on that kind of model, we are able to get 88% on train, 75% on test, and that model also was developed on Hasty, so we do not have yet the scaling for that, and the scaling will actually be in the image classification. So we hope to actually see an improvement in the attribute recognition using scaling in that model. So image classification, that one is basically one model per species, per attribute. So that's quite a lot of model. A lot of computing power, I would say that's one of the big drawbacks, but one of the big advantages is actually the flexibility that we have to develop those models, because we can apply different architecture, different type of parameters, different transformations for each species and each attribute of the species. In terms of the accuracy, and remember here we do have the scaling in this case. For all the model, the average accuracy is about 70% on test, on foot, 92% on sex, and 87% for the individual identification. And all of this is from the test set that we have. So we are able to identify, especially for the sex and the individual, quite clearly which animal, which species it is. The foot, I think, is that's where I think the scaling would be interesting to have. But in this case, we found that the scaling was not necessarily helping that much more. The 70%, I think, is we can detect the left and right quite clearly, but when it comes to front and hind, so the rear, it gets a little bit more tricky because they're very similar in look, and we're hoping that potentially applying each image segmentation would actually be potentially improving, and that's one of the advantages of doing image classification is we can basically create different models for each of the species. This leads me to inference. That's what we're all companies are about, is how do you push this to production, and what do you do with it. So in our case, here in this case, we have a picture of a footprint. So you can do that through a phone or things like that if you push to production that way. And we would detect basically in this case that it's a lion, an African lion specifically. And we are sure at 93% or something. And then we also detect the attributes from that footprint. In this case, it's a male, it's rocket, so it's specifically rocket, and the left hind, so the left rear foot. And these are actually extremely useful for us in terms of gathering that data. If we were comparing, it's basically doing a census of all the footprints we come across, gathering that data, understanding their behavior without impacting them, without interacting with species, so without changing their behavior. And that data is useful to also know how many species there are out there, which area they are in. You would think that we know where they are located everywhere. For example, cheetahs, which are very well known and very well researched species. We actually, in Africa, have a hard time understanding where they are located or in what amount. There is a lot of gray areas on the map. And basically doing that kind of work help us understand this better, their numbers. These are endangered species. If we can understand better their number, this will help a lot. And also apply this with the help of organizations, but also governments, to change policies to protect those species from extinction, and as it impacts on our environment as well. And I wanted to thank Hasty for inviting us today, talk about this. It's a big, interesting project for us, and we hope you liked it, and also thank you for them for their support. And there is the website right below if you're interested to learn more, and my email if you have any questions as well. Thank you.
Yeah, thanks so much for that. I think it's a really, really interesting use case, and it's fascinating how much you can see like in a footprint. It's like I never would have thought that, right? It's really cool. And also I think it's interesting how how you chain models. It's actually a prime example of where you often would start a project with, hey, yeah, let's just train an object detection model and reclassify all of that. But in reality, more often than not, you first do one task, then you do the next one, and like with the attributes and with the scales as well, what you're talking about. So it's a very interesting use case in that sense. But for me, actually, the question would be, so I know this is still kind of research, but essentially, what are your plans going forward for rolling this out? Do you know how you want to approach that? Who's going to use it? Can you say anything about that, maybe?
Sure. I mean, like I mentioned, the first thing is pushing this to actually production. This model flow was just we just finished it in May, so it's quite recent. The previous model flow was quite different as well, but we're hoping to push this to production. We are actually hoping also to apply a lot more pictures because, like I said, we have about 3,900 pictures for this model, so, and we are hoping to get to use those 10,000 more images. And what we are trying to first do is push this production. We have an app that is a mobile app that is coming out soon that we are hoping to gather even more data with the use of the advantage of having people helping us gather data. So that's kind of the main goal first, is gather more and more data. And the next one is basically pushing this further. We are hoping to, we did recommendation to use LiDAR. We used also using UAV. So one thing would be to try developing further the techniques that we're using for UAV imagery, which are quite different. We might not be able to do footprints with that, but we can do potentially the tracks and the animal as well. So it's we're trying to push this, and then using this with organization to protect the species. That's and hoping governments and local or national can change certain law in order to protect them, basically.
Awesome, very, very cool. Thanks for that. Yeah, that's it with the event. That was both talks. Thanks for everyone that tuned in. And yes, exactly. If you have any questions about Hasty, about what we do, so you just find us hasty.ai. My email address is tobias@hasty.ai, or you just find the contact form on the website. And we are always happy to just have a chat and talk about what. It's always exciting to learn what people are working on and to see if we can help, how we can help. And maybe just give some input, some ideas. So feel free to reach out at any time. And yes, we will also let you know when we do the next event. Bye-bye. Thanks.